Okay, so today we're going to continue our segment on probability. We're just adding to our platter of probability laws, if you will. And again, I hate to just be reading out of the book to you, but sometimes you got to read the book. So let's make sure we're tracking all of our formulas and theorems. So for starters, I'll read this. Conditional probability. Notation, P, and I'll even write it off here. You'll see this notation, F with a slash and then E. That's read as probability of F given E. So that notation is read as the probability of event F given that event E has occurred. So it's the probability that event F will occur given that event E has already occurred. So that's our conditional probability notation, okay? Just hold that thought. We're going to play with that in a moment, but something to wrap your head around. Suppose I was interested in the probability that someone voted for Obama given that they were a woman. Well, see, that shrinks the sample space. So I'm no longer looking at everybody that voted for Obama. I'm only looking at the women. And, perhaps that conditional probability would be a lot higher than the probability of voting for Obama in general. So that would be interesting, something to compute. Okay, hold that thought. Let's keep looking. Okay, so remember, the way your book is, we want to look through and find everything that's in these magical boxes that are in your book, right? Because they're probably important, so I'll circle the next box. Conditional probability rule. Okay, and I'm not sure how big the font is, so I'll rewrite it. The probability of F given E is equal to, so I'm reading this part here, is equal to the probability of E and F, but I'm going to write it mathematically. The probability of basically F intersect E divided by the probability of E alone. Okay, so, and you can see it here. I wrote the math symbol for and. Remember that intersection symbol means and. So the probability of F given E is equal to the probability of E and F divided by the probability of E alone. Okay, so I'm zooming in on that. All right. You say, well, how's that going to help me? Well, we're going to see that in a moment when we start doing these problems in your book that I'm going to select. Okay, now we also want to take inventory of another rule, the general multiplication rule. And this says the probability of E and F, I like to think of that as the probability of E intersect F, written symbolically, is equal to the probability of E times the probability of F, given that E has already occurred. So we'll also see how to sort of utilize this rule here in a moment as well. Okay, and the last two lovely boxes before we actually do some problems together, we want to take special note of this, which basically says if small random samples are taken from large populations without replacement, it is reasonable to assume independence of events. That basically means, if I use the multiplication rule for independent events, probability of A times the probability of B, basically means I'm not going to get something drastically different than if I took the probability of A times the probability of B, given that A has already occurred. So it says as a rule of thumb, if the sample is less than, thing you want to remember, is the sample is less than 5% of the population size, we treat the events as independent. Okay? And we'll delve deeply into that in a moment. Two events E and F are independent. This is a good one to know. If the probability of E given F is equal to the probability of E alone. Or equivalently, if the probability of F given E has occurred is equal to the probability of F alone. It says if either condition in our definition is true, the other one is as well. So, you can sort of just check one of those if you're checking for independence. All right, I think we're ready. Let's try some problems. So you see I'm at the assess your understanding part. So I'm just picking a few problems with you here. For starters, number 4. And it says, suppose that E and F are two events, and suppose that the probability of E and F is equal to 0.21, and the probability of E alone is equal to 0.4. And then it's asking, what's the probability of F given E? Well, with these kind of sort of abstract equations, where you don't have any context, your gut instinct says, well, boy, I wish I had a formula that I could sort of plug all this input into and sort it out. And you do, because we just mentioned it a moment ago. So hold that thought. Okay, so the first thing I do with this kind of problem is I think, all right, what kind of formula do I have that's going to relate all these kinds of events? So again, I wrote down all the critical information. They're giving us that the probability of E intersect F is equal to 0.21. They're giving us that the probability of E alone is equal to 0.4. And they're asking us to find the probability of F given E. Well, earlier we said that the probability of F given E will equal to the probability of F intersect E, or F and E, you could say it that way, divided by the probability of E. Now the good news is, I always think like in algebra, given, given, find. Let me do this in another color here. You've got your givens and you've got your find, You're trying to figure on this. So you wish you had something to plug here, and you wish you had something to plug here, the probability of E, and you do. So 0.4, you're just going to plug it in for the probability of E, and 0.21, you're going to plug that in for the probability of the intersection of the two events. And you're just going to compute that. So you say, okay, so I'm just going to take 0.21 over 0.4. And you can literally type that out. So 0.21 divided by 0.4. And hopefully you're thinking that's 0.525. All right. So now if I go back to this problem, I'll zoom in. Number 4. So the answer to that one was 0.525. All right, so again, I'm just always grabbing these relationships and sort of plugging and chugging in the things that I know. Okay, let's try again. Okay, now recall that sometimes the author is, going to switch the language up on you. So let's go ahead and try number 7. It says, suppose that E and F are two events and that the probability of E alone is 0.8. And the probability of F given E is 0.4. And then it says, what's the probability of E and F? Well, the thing is, I can't answer those things unless I have those relationships memorized that we talked about before, or at least if I understand those relationships. So let's start there. Okay, so what I always do, I write down my givens. So I've got the probability of E is 0.8, the probability of F given E is 0.4, and the probability of E intersect F is what we're looking for. So the first thing I do then is write down my relationships that I know exist. So we know the probability of F given E is equal to the probability of F intersect E, or E intersect F, you could say it either way like that, divided by the probability of E alone. Okay. The main thing is, notice that whatever's after the slash in the given is the thing that's in the denominator. Notice that. Okay. So I write down that, then I think about, okay, what things do I know? Well, the probability of F given E you actually know. That's 0.4, so that means I have to plug it here. Okay, so that means 0.4 equals, and then it's kind of like algebra from there. This is what you're looking for. The probability of F given E, that's what you're, F intersect E, that's what you're looking for. That's kind of like your X. Okay? And the probability of E alone, well, that's given, that's 0.8. So I plug it in. Okay? When I arrive there, I'm sure you remember from algebra, if you're going to solve for X, you're going to, a lot of people say, multiply by 0.8. So, okay, let's do that. Okay, so if we do that, if we just take our, 0.4 times our 0.8, sort of like cross multiplication, we'll see that the probability of F intersect D then is 0.32. So again, a lot of, especially these first, 8 problems, are just manipulating that relationship of conditional probability, the fact that the probability of F given E is equal to the probability of F intersect E divided by the probability of E alone. So you're often sort of reciting this relationship and plugging things into the right position. Okay, let's try another. Now, because what we did there was so abstract, I wanted to pick something that's like more realistic, something we could wrap our heads around, right? So we'll typically have these tables with data, right? So driver fatalities. The following data represents the number of drivers involved in fatal crashes in the U.S. in 2009 by day of the week and gender. So here we have the days of the week, and here we have gender. And then we have our row totals and our column totals. So we can see that, the total number of people surveyed was, 75,000 some. Now for time's sake, I'm just going to do part A and part B with you. So it says among Sunday fatal crashes. That means given that we're only looking at Sunday fatal crashes, what's the probability that a randomly selected fatality is female? So what you're doing is you're shrinking the sample. That's kind of a way, let's get used to the language. Given Sunday, sometimes they'll say, given that it's Sunday, what's the probability that a randomly selected fatality is female? So you're really just shrinking the sample space to Sunday. So, the 12, 5, 4, 7 will be what goes on the denominator, and then you're looking at the females, and you're saying, okay, 4, 3, 2, 5. Now let's go ahead and crunch that out. I'll do it with you. 4, 3, 2, 5 divided by 1, 2, 5, 4, 7. We can respond in a decimal form. So hopefully you're getting about 0.345 rounded. So that answer to that first one is about 0.345. Okay? So this is related to conditional probability because we're shrinking the sample space. We're saying given that it's Sunday, what's the probability that the randomly selected fatality is female? Now look at how they switch you on the next one. Now it says among the female fatalities, what's the probability that a randomly selected fatality occurs on Sunday? See, now, I'll erase this. Now you're saying, all right, given, let me erase all these strokes here. So in part B, we're saying among the female fatalities. So now we're shrinking the sample space to only looking at the female. So it's really a matter of, what are we going to put on the denominator? So now we're only looking at the females. So given that you're only looking at the females, so 2, 5, 7, 5, 9, what's the chance that the fatality occurs on Sunday? And now you're looking up the Sunday, and you're seeing the 4, 3, 2, 5. You see? So you get a different fraction based on what it is that is in the denominator, right? So 4, 3, 2, 5 divided by 2, 5, 7, 5, 9. So hopefully with that, you're getting about 0.168. So for part B, 0.168. So the biggest thing I can say is when they say something like among the female fatalities, comma, that means that you're shrinking that sample space. You're not looking at 75,000 some people anymore. You're only looking at the females. So you're shrinking that sample space. That denominator is going to be smaller than the entire sample space. You're shrinking it to just looking at the females. Okay, hope that helps. Now we're going to try one more section of notes. Actually, I just decided that I'm going to create a totally different podcast for the next section of notes, which is counting techniques. So I just decided instead I'm just going to take a look at this last question here, C, part C, with that same fatalities question. So it says, are there any days in which a fatality is more likely to be male? That is, male given Sunday versus male given Monday. Well, the answer to this question is no. And, one way to do that is, given that it's Sunday, okay, take a look at, fatalities, that are male, given that it's Sunday. So, for example, you would want to compare 8222 out of, 12547 versus, and then compare 6046 out of 9154 and just see if they're statistically different. So, 6046, take a look at their decimals out of 9154 and see how much they differ, if it's significant. So 6046 divided by 9154, the decimal on that's 0.66, 66%, versus, crunch the decimal on that, is also 66% if you round it. So, what we would say is that's not, significantly different given the day that it falls on. So that would be the answer to C. And like I said, you could do that for every day of the week and see if there's a significant difference. Okay? Hope that helps. Good luck.